I wanted to start by saying that actually I taught 4,000 probably at least 25 times in the 90s when the ethical issues were very, very different. But I do recall a number of things about teaching ethics to computer science students and the challenges of getting them to engage with this. So several things have struck me so far in what Ben and Ellen have talked about. Okay, and what is going to be talked about actually soon, which is case studies. So one thing one thing I was thinking about was I can imagine many of you are thinking, oh my gosh, how in the world am I ever going to get ready to infuse all these really interesting things into my class? This takes a lot of time and it's a lot of overhead. And the class is already, designed, so why should I do this? So one thing to think about is there are three pedagogies that are actually being discussed here today, and they are different. The first one we've heard about already is simulations, okay? Simulations is when you design a scenario in which there are various roles that people can take on. And the reason you would do this kind of pedagogy is you want students to understand the complexity of a particular situation, or what Roberta Berry called fractious problems, problems that have many sides, many perspectives, many ways to think about them, and many stakeholders. So it's possible that that's important for you from a cognitive perspective to help students practice taking on different stakeholder perspectives. And if that is your goal, and it's a laudable one, then simulations are the kinds of pedagogies that you would consider. And you just need to find a scenario that has various personalities, various stakeholders that are very, strongly committed to a particular perspective, and have students try to take those on. Now, when I think about that as a learning and cognitive scientist, what it does, it opens up to the students this idea that, geez, whenever I am designing something, there are going to be different stakeholders that are going to respond differently, potentially, to my design concept. So that is actually what a simulation would be for. And those are extremely valuable. And I thought it was fascinating what Ellen was saying, that they don't want to take on the technical roles. But the other thing that's really interesting to me about this and the simulation she put them into is it illuminated the fact that you could be put into a position as a designer where you are actually taking people's jobs away. And it's interesting for young people, that realization is incredibly important for them to have. So that's a value of potentially a simulation. Now let me go to case studies, which are going to be talked about after me, because I think, it's really interesting to understand the value of each one of these. I think of a case study as a forensic activity. There is a case. It has been determined. There were players. Things happened. And so what the students do is they go in and they forensically excavate the sequence of events, the timeline, and the decisions that were made at different points. And so that's a very useful cognitive activity. It's one that's used widely in law school and widely in MBAs, because the function of a case study is to have students see or have ways of thinking, cognitive strategies, habits of the mind of a particular group of people become available to novices. So a reason to use a case study in the context of 4001 or any kind of class would be to illuminate the kinds of cognitive strategies that expert ethical designers make or failed to make, because it's just as useful to illuminate cases where bad decisions were made as to illuminate decisions where a bad decision was headed off at the pass. So that's a reason to use those. Now I'm going to get to problem-based learning, which is what we do over in biomedical engineering. So problem-based learning is a pedagogy that was developed in medical school education probably 40 years ago. And the reason it was developed was very specific to the situation of medical school education, but not necessarily not specific to other instances. So here's what was going on. For 2 years, medical students would sit in classrooms and memorize voluminous amounts of information that was being thrown at them. And then suddenly in year 3, they're in a clinical setting and there's a patient who says, "Doctor, every morning I wake up, my eyes are yellow and my ankles are swollen. What's wrong with me?" Well, guess what? These medical students were completely incapable of responding to that situation. That's because they had not practiced the cognitive strategy that doctors use every day, which is diagnosis, or what we call hypothetical deductive reasoning. So because they hadn't practiced that, they didn't know how to think through, how am I going to diagnose this patient before I can even think about a treatment strategy? So problem-based learning was developed in response to this dilemma, which was costly because it would take 8 months probably for students in the clinical environment to get up to speed, and it was dangerous because they had a lot of people running around who had no idea what they were doing. More importantly, they were not in the first 2 years building what we call cases. These are cognitive cases. So experts are really good at what they do. And if you've ever watched the TV show House, where he's the fantastic diagnostician, and the reason he is so successful is because he has hundreds and hundreds and hundreds of cases in his repertoire. And so when a new patient walks in with a series of symptoms, through analogical reasoning, he maps what that patient is telling them and the data that is being collected through tests onto many of the prior cases he's had until he finds a number of matches, and then hypothesizes it could be this, it could be this, it could be this, and then through the acquisition of more and more data eventually settles on a diagnosis and then a treatment. So the reason I'm telling you this is that is an instance of case-based reasoning. So if you're an expert, you have lots of cases. So Ellen is an expert computer scientist, and she probably has lots of cases where she had to go in and design a system or something like that. And so she doesn't do this from scratch. She does it by leveraging previous cases she's already solved and said, well, this is a lot like this, and this is a lot like this. So one of the reasons, a second reason for using problem-based learning is to build a case file for your students. So when they face new cases as experts in the field, they have a variety of cases to use as a repertoire to begin to say, well, is it like this? It's like this, it's like this. So problem-based learning, or what we in biomedical engineering now call problem-driven learning, is very different from a traditional, well, we're going to lecture for a few weeks and the students are going to do a lot of homework and then we're going to give them a project. So that's a pretty typical thing to do in probably computer science. They have many, many weeks of lecturing, they have lots of homework sets, and then there's a project. Well, in biomedical engineering or problem-driven learning, you're reversing that. In day one, you give the students a challenging problem. And they have not taken courses that will give them answers to how to tackle this. They don't have the answers, but you're going to put them on a team, and that team is going to work for a certain number of weeks until they have deliverables. And those deliverables, every set of deliverable that you're going to ask them to create are the kinds of deliverables that they would have to create if they were actually in real jobs, okay? So in the case of biomedical engineering, we try to create what is almost like a simulation of an internship. I mean, that's the only way to describe it. Because when your students go off and they have an internship at Microsoft or they're in Google, no one's going to hold their hands. They're not going to be looking at problem sets. They're probably going to be given a pretty, open-ended, ill-structured problem that they're going to have to deal with. So the question is, how do you get them ready for that kind of thing? How do you give them the cognitive strategies, the cognitive skills that will get them to a point where they have a certain level of comfort of, geez, I can take that on. I can do that particular thing. So if you're interested in problem-based learning, the first thing you need to do is figure out what is your cognitive model? What is the cognitive strategy that you want students to practice as expert data scientists, as expert algorithmic designers? In other words, how do you put them in that environment where they practice what you as an expert already have managed to develop as a cognitive strategy? So going back to medicine, it's hypothetico-deductive reasoning or diagnosis. Actually in computer science, it would be troubleshooting. So I remember being in computer science when I would hear the faculty complain all the time at how poorly the students were able to do troubleshooting. So maybe what we want to do, and I'm sorry I don't have my slides because I actually have a picture of different problem types from very well-structured to very ill-structures that starts with algorithmic problems and goes all the way up to dilemmas. And actually troubleshooting is right in the middle there. Because if you think about troubleshooting, how does an expert troubleshoot? Well, you collect data, quote unquote, and from that data you set up a series of hypotheses. It could be this, it could be this, it could be this. And then with those 4 or 5 hypotheses, then you have to collect more data. So imagine that you actually gave an exercise pretty early in the semester that the code isn't working. Okay, so-and-so, is a client, they've called up and something's wrong with the software you sent them. Here's the software. And you throw that at them and they have 3.5 weeks on their teams to come up with what they think the origin of this problem is. So that would be an instance that I could think of pretty easily in terms of troubleshooting and having them practice that particular cognitive strategy, which is really important for computer scientists. So the ones that Ellen has talked about where you've got built into an algorithm, you have built into an algorithm a kind of bias. And that bias is disadvantaging certain people and advantaging other people. So, the way you could deal with this is you could lecture on it and say, okay, there's algorithmic bias, and we know about this, and we know about this. But if you were to do problem-driven learning, you turn that somehow into a problem. And actually, Ellen gave a really good example of that, I think it was Ellen, who said, invent a different algorithm, okay? Invent a new algorithm. Was that you, Ben? One of you said that. Which one was you?
It was Ben.
Okay, I would consider that that is beginning to get into, you could say, okay, there's a problem with this algorithm, and it turns out that folks with disabilities are being disadvantaged. Invent a new one, okay? And you would give it to them on day one, okay? So there wouldn't be a lot of lecturing up front. There would be like, here's the problem, get on it. So with problem-based learning, there's a cycle, okay? There's a very strong cycle. You get the problem at the beginning, and then the team identifies immediately everything they need to know that they don't know right now. So they generate a list of research they need to go out and do, okay? Or tasks they need to go out and do. So if it's a troubleshooting situation, they would have to identify what do we know right now, what do we think the problem might be, what kind of research do we need to do, and let's go and do it. And then the team breaks up, everyone goes out and does research, and they come back together. And now, with more information, they share that information. And they say, here's what I found out, and here's what I found out, and here's what I found out. Now, it's interesting, in biomedical engineering, we designed special PBL rooms for this. Now, these special PBL rooms are 10 by 10, little tiny war rooms with writable walls to the ceiling, okay? Those are magnificent. But guess what? During COVID, we didn't have those. Now, think about that. Think about, did that destroy our ability to actually do problem-based learning? And the answer is no, it did not. Because we leveraged all kinds of technologies in teams with whiteboards and everything else to basically achieve the same kind of thing. So the algorithmic one is a really interesting one. I know that in our biomedical engineering, one of the first courses we teach, actually it is the first course in biomedical engineering, one of the problems we give our students, and it's not really a problem, it's really a case study, is go out and find an instance in biomedical engineering where decisions were made and certain populations have been disenfranchised or marginalized or not being paid attention to. So instead of giving it to the students and saying, why did this happen? We say to them, go find one. And that's interesting because, you know, if I were to, one thing that I kept thinking about when both Ben and Ellen were talking was, why do this? I mean, what is the reason to do this? Well, you could say, well, the reason we're doing this is because we want to create ethical engineers and computer scientists. But actually, I think there's another even more important reason. It is motivating to the students. The students want to be taken seriously. They want to be put in a situation where they're giving something authentic to talk about, to address. And so a reason to bring these to their attention, it's as I say it is empowering them. Because when you hold back and say, well, you're not ready to make decisions about this, or you're not ready to have a discussion about this, which is the typical mode in higher ed, is you're not ready to until you get to capstone design. Oh, okay, I guess you're ready to now. You know, I think that we have to say early and often, you are ready to. And particularly because of our Georgia Tech students who are exceptional. So with that, I'm going to stop and answer any questions.
Fantastic, Wendy. Thank you so much. I wrote a bunch of stuff in the chat just because I was kind of, I don't know what, making you slides on the way, capturing some of the key concepts. And let me say, I think one of the so Wendy is a cognitive scientist, and it's what one among many things that stood out to me in your comments were the sort of bringing us back to cognition and to what it is we're really trying to get our students to learn, and how important that is, that we make that quite foreground that as we're making decisions about what we do and how we do that, how we go about it. Desayo, thanks for the.
I mean, that is really critical, because when we first developed it over in biomed, we had a series of 3 problems, and this is something to think about. We had 3 problems that had a problem core, and the core was, we want students to develop these strategies, these ways of thinking, and these cognitive mental models of how to think through something. And then we would put different skins over that core. Okay, so this is the trick with this. If you develop your cognitive core of what do we want them to practice cognitively, do we want them to practice analysis? Do we want them to practice trouble? Do we want them to practice decision making or, evaluation. Each one of those is a cognitive, it entails a certain number of cognitive steps and strategies that if you want them to practice those things, that should be at the core. I want them to practice evaluation. So they have three systems they could implement. Okay, I have 3 computer systems they could implement. You decide which one needs to be implemented. Now that's a pretty complex problem. Okay, and it has so many ramifications because if you think about Bloom's taxonomy, everything underneath it, they have to have the deep conceptual understanding. They have to be able to do analysis, and they're doing diagnosis, and then they're doing evaluation. So, that would be a very high level kind of problem to ask students to evaluate 3 systems and choose one, because there would be so much that would have to go into that. But the thing is, if you can get these core problems and just put different skins over them, and the skins are in the newspapers every day, okay, there's a new problem on the horizon around, algorithms and problems with algorithms. Okay, put a new skin on top of it. And that's what we did. And it got to the point where it was really easy every semester is the students experience new problems every semester, but we knew at the core they were practicing very specific, cognitive skills that we wanted them to practice. So yes, I heard both of you talk. Of course, I was pulling the skin off and I was thinking about what's the cognitive strategy would be necessary, but that's where you need to start. If you're going to do problem-driven learning, you have to ask, what are the cognitive skills that we want them to practice here? And given those, what kind of problem do we need to give them that is going to force them to actually do that, but we're going to put scaffolding in place to make it possible for them to